Sorry, you didn't turn on the microphone.
So good morning. So may I see the video? May I see your face? Good. So I wish, you see, someday when we met, you see, bump each other on the street, I can recognize, oh, this is my student, right? Okay. Let's start. We said this course is dealing with Maxwell equations, and 4 Maxwell equations are coming from experiment, not mathematical derivation. But however, the mathematical form is so elegant, okay, and then even you'll find surprisingly it's so simple, okay, it's so simple. And let's take an example. Let's take this Coulomb's law as an example, right? So Coulomb's law, what Coulomb's law says, okay, if we put a charge, okay, at somewhere in the space, okay, then the charge, that means the static electrical field. Then we expect to see electrical field line excel, okay, outward, right? Then how we can sense the existence of the field is if we put another charge, okay, if we put another charge near this first charge, then the second charge will experience a kind of force, right? And if the charge is same property, let's say all positive or negative, then we can experience the force excel, right? Appealing, repels the 2 charges away, right? If they're the different properties, then they attract to each other. So that is the force we can measure, right? Then we can measure at the end. People come up such elegant equation, okay? Sure, we can measure the force is proportional to the quantity of the charge, right? Q1 and Q2. And then we can say, hey, this is proportional to the quantity of charge with a certain constant we can define, okay? But the question is, how do you know? How do you know this is a function of 1 over r squared? How do you know this is 1 over r squared, right? And this really is an interesting question, right? And to answer this, it's difficult for us to have a physics experiment to repeat this experiment people develop, okay, to find the Coulomb's law. But we can repeat this experiment using computer simulation. Okay, what this computer simulation is? Okay, take a look what the computer simulation is. If I put a charged conductor sphere with radius of 1 millimeter, I try to make it very small, okay, with 1 millimeter in radius. This is a sphere, okay, this is sphere. So the reason I chose sphere is the charge on the sphere must be uniformly distributed, okay, uniformly distributed. Then what I do 3 things, okay. I calculate the electrical field, okay, along the z-axis. You see, because that equal if you go along any direction, because this is sphere, right? So I just arbitrarily pick a convenient direction along that axis. Okay, so this is EZ. Okay, this is what I calculate. Okay, then I calculate along the z-axis, but with a different distance. So you see, I calculate start from slightly away from 1 millimeter. All right, so very close to the sphere. Then I gradually increase the distance. Okay, first I come to 5 millimeter. Right, then I collect all my measured data and I curve it using Excel. Okay, Excel has a feature, you choose a function that do the curve fitting for you. Okay, then I can find out that is a function with exponent 1.9828, not 2. Okay, suppose here is 2, right? So ideally, this is 2, right? And so ideally, this is 2, okay, in our equation. But if you really do experiment in the narrow region of the field, you find, oh, this is 1.98. Okay, then let me extend this distance from 5 millimeter further away to 30 millimeter. Okay, then I have more data, right? Then I have more data. Then I fit again, and then I curve fit again. You see, this number is approach to 2, but not equal to 2, right? Not equal to 2. So that means the experiment never can come to such accuracy. You see, this give us, you see, that in the 3rd or 4th decimal place, even give you 100 decimal place, you still don't know if this is equal to 2 or not, right? Not mentioning that experiment was done, you see, more than 100 years ago. So what is the conclusion? What is the conclusion? You said, okay, this is the first experiment I did. It's a sphere. Okay, it's a sphere. So let me do another experiment. I don't do sphere because you never can make sure, you see, you have a perfect shape of your charge. Okay, perfect shape that can accumulate charge uniformly, right, in a real physical experiment. So what we do is I use a small cube. Okay, I use a charged small cube. So if this is a cube, for sure the charge never be uniformly distributed. I repeat this experiment. Okay, then you'll find this exponent value slightly away from 2. Okay, slightly away from 2. But if you, okay, so what you can do, so if you did this experiment, can you draw the conclusion the same as Coulomb's law? Maybe most of the people won't. Oh, this is not equal to 2, right? Not equal to 2. Okay, so what so far since the Coulomb's law discovered, right? So far, nobody can find any counterexample. Okay, say this is not accurate, not mentioning this is wrong. Okay, this is not accurate. Nobody complain. Have you ever heard anybody complain Coulomb's law? If Coulomb's law is not right, all the Maxwell equations is not right. Okay, so this is interesting, right? So what observation, we have. Okay, the observation we can have from the experiment. Okay, so first, there's no ideal function that can fit all the cases. Okay, no ideal function. Let's say 1 over r squared. This is a very ideal function. Okay, so it depends on the shape and the charge, the size of the charge, right, and the distance. Right? Okay, so you never can derive accurate. You never can derive accurate result from experiment, no matter what. Okay, so what we have to make is postulation. Okay, so what is a postulation? So that English word maybe not frequently used. Okay, what we frequently used is assumption. Okay, the word assumption is close to postulation, but essentially different. Okay, postulation means it is assumption, but we believe it is right. Okay, we believe it is right. So this is a research methodology. Okay, so I'd like to take this opportunity to discuss this. Interesting, right? Okay, so postulation is a very good research approach. We use this very often. Okay, so we make assumption first, then we justify it. Okay, it is correct. Okay, then the last thing is, in most of the time, okay, the real behavior, the mathematical description of a nature phenomenon usually is a very simple function. Okay, you won't have a function like r 1.9998 something. This is for sure. They won't be a nature. They won't be the nature. Okay. This is just a side story. But the good thing is we touched something about Maxwell equation, Coulomb's law. Okay. So when we have a Coulomb's law, just now that expression, we used to use 1 over r squared. That is high school stuff. Okay. So we should use, learn how to use more general compact form in either vector or a complex number, right? Okay. Now, if we describe it for arbitrary point, the source point, and the arbitrary field point, okay, one is a field. Then we know we can use position vector, we can describe things. Okay, then we can use distance vector to measure the distance both in direction and the magnitude, right? So in this case, we can use distance vector, the magnitude of distance vector, okay, to measure distance from the source and the observation point, right? And then in order to describe the direction, okay, that is pointing from source to the field point, we can use vector, okay? This part basically describes a unit vector. Then you can see vector is a very, very useful way. Okay, if we use this vector expression and then it's general, okay, concise and clear, and definitely absolutely accurate, you have no any ambiguity. All right, so the convenient is once we have this general expression, we can express the total electrical field generated by multiple charge point, discrete charge point, right? It's just a linear superposition. Okay, just a linear superposition. All right. Now, once we understand the expression for discrete charge system, then we can convert it to the cases where the charge is continuously distributed, right? If the charge is continuously distributed along a wire, okay, say, oh, this is a charge, okay, with a certain distribution, I call rho L, that is a function of location, then we can find the field at any point, okay, by integration, by line integration, okay, or if the charge is distributed over a surface, then we have 2D case, so this integration become surface integration, okay, or volume integration, okay, if charge is distributed over a volume, okay. Then this is the basic property of static electrical field. So once we have defined the field, electrical field, then we can define a very basic quantity we call capacitance. Okay, the capacitance is defined by this. This is definition. Okay, so what that means is if we have one conductor with a total charge Q, then if you have another, you find another conductor, okay, that contains total charge is a minus Q, then you can find what is the potential difference between the two. Okay, we will mention what is the potential difference. We will review it later. Okay, then suppose this is a voltage. Okay, then we define the quantity C. C is Q divided by V. Okay, the capacitance, basically the quantity of capacitance described. If I consider these two conductors as a system, so what that describes is the ability that can hold charge. Okay, that can hold charge. Say, for example, right? If the capacitance is high, you give a very small voltage difference, you can have a larger amount of Q hold up by the system, right? Okay, so right now, what I illustrate here is only two conductors. What I emphasize, this definition. Okay, look at that definition. You may say, oh, I learned this in high school. You don't need to repeat. Okay, if I don't repeat, let me ask you one small question. Simple question is, if I have two conductors, okay, this is a Q1, okay, I have another conductor. This is a minus Q2, okay, but the Q1 not equal to Q2. Then I can find the voltage V. Tell me what is capacitance? Tell me what is capacitance? The capacitance should be capacitance equal to Q1 over V or Q2 over V. So which one is right? All right. Okay. So I leave this question to you, right? Okay. And another question. If I have a tree system, three conductors, how do I define capacitance between them? How do we define capacitance? Of course, you see, for such a system, if this is a conductor, okay, so I have three conductors. Then each conductor, you have, if this is 1, 2, 3, each capacitance, each conductors, you have capacitance to ground. That means at infinity. Okay, then that is self-inductance. Then also between each conductor, we have a mutual capacitance. That is capacitance level if we have more than 2 conductors. Okay, so capacitance exists between, as long as you have conductor, you have capacitance. Even though you have one conductor, you have capacitance. This capacitance is relative to the ground. That ground either near you, okay, if you stand on the earth, or if you in the space shuttle, so the capacitance goes to that ground at infinity. Okay, so even one conductor, you have a ground. Once you understand this, you will understand a lot of electrical properties or phenomena. All right. Okay, I show 2 examples. You see, one is touch screen. Okay, touch screen. Sure, there are different mechanisms to build touch screen, but you say, but capacitive type of touch screen is a very common touch screen, right? Okay, what the mechanism is, you see, they have a driving electrode. Okay, I have driving electrode. Then they have a receiver electrode, the electrode. So between these two, suppose you have a one capacitor, Cx. Oh, by the way, you see capacitance according to definition, it is independent to the voltage it applied and independent to the charge you applied. Why is this? You will say, hey, you look at the definition, this is a Q divided by V, right? Why you say it's independent to V? Because, okay, because of this. You see why it's because of this? Or if this is not clear, let's look at this. Let's look at this. What V is? So V is the integral of electrical field. So we will say it later today, right? That is electrical field to line integration. Okay, the electrical field is proportional to the voltage. Oh, sorry, not proportional. The electrical field is proportional to the Q. Q, that means the V is proportional to the Q, right? V is proportional to Q. So when the V is proportional to the Q, if you say this V is the Q times something, what is this? This is equal to 1/Z. Okay, then you can see the capacitance. The the capacitance is really only depend on the geometry, the structure, the property of the conductors. All right. Then once we define these two electrodes, okay, once we define these two electrodes, driving electrode and the receiver electrode, okay, the capacitance Cx is determined. Cx is determined. So that means, okay, if I apply a signal to the driving line, what signal I can receive on the receiver side is determined because the signal is coupled by the capacitance. Okay, but once your hand touch or close to the driving electrode or receiving electrode, so you introduce another capacitance, your body, and also you introduce a capacitance because your body is a very big container of charge. Okay, big container of charge. So once you have the network change, circuit change, when you're driving a signal to a driving line, the signal coupled to the receiver line, because capacitance is changed, so your signal received is changed. So that the IC can detect. So something changed, that means that something is touched on the screen. Okay, so that is a one application. Right. So the second application, let's see. We all know importance of ICs. Okay, the importance of IC. Then the importance, when we build IC, we know we have to have gate that must be electrode. That must be metal electrode. Okay, then we have a source, we have a drain. All this over each of region, how the signal is controlled by applied voltage and current that goes through the conductor. No matter how small it is, okay, you exist all those capacitance, okay, between gate, drain, source, and so on. Okay, so of course, once the feature size of IC is small, the capacitance is small, then in fact, this we call parasitic capacitance become less, but that still exists. Okay, don't forget, you see, in the circuit theory, what we deal with is the impedance. So what the impedance is for inductance, for capacitance, we have J omega C, right? For inductance, we have J omega L. Okay, so that means if the C is very small, but if omega is very high, this impedance is also significant, right? It's also significant. So that means no matter how small it is, the circuit, the frequency, the data rate always increase. Okay, in our application. So all these capacitance never can be negligible. Okay, never can be negligible. Okay, so that is the reason you see the capacitance is a very important concept. Right. Okay, from the formula of the capacitance, this is a, okay, let me interpret equation 1. Okay, equation 1, that's suppose C, suppose it equal to total charge Q divided by voltage, right? Then let's take a look, what is this? Okay, the epsilon, we know this called permittivity, right? Permittivity. 1 epsilon times electrical field intensity, E. This result is we call electric field flux density D. Okay, flux density D. So when we have D dot, this is a differential area, right? Differential area. That means if we have a surface, we find a very small patch, then we define its normal direction. Okay, so this is a small area combined together. This is ds, right? What's it ds? So first of all, ds is defined by a normal direction of a surface, normal direction, right? So when we have a dot product of a direction, then with a vector, what we are doing? What are we doing is we take a normal component, because dot product is result a scalar, right? Result a scalar. So what's that equal to? It's equal to a normal component, and then multiplied by the total area. Okay. So what is the normal component is? What is the normal component? The normal component exactly equal to the charge distribution. This is charge density. This is charge density. Now we understand. Okay. Oh, now we understand. This is you collect all the charge over a surface of conductor, because the conductor, giving a conductor, the charge only exists on the surface, So that means this is the total charge. Okay, this is total charge. Right. So what is this? Just now we mentioned this is basically the voltage. Exactly. So electrical field integration, line integration, that equal to a voltage. That equal to a voltage. All right. That equal to a voltage. So that is definition. Very, very interesting thing is, in addition to capacitance, there are three basic components. One is capacitor, one is inductor. What is third one? In your circuit theory, what is the third component? Come on, give me an answer. You have no answer? Oh, yes, resistor. Yes. Somebody answered. Okay. Third one is the resistor. We only have these three basic components. So that means the double E is a very simple subject, right? We only need to deal with three components, no matter what you are doing. Okay. So the resistance, how resistance is defined? Okay. The resistance is defined by voltage divided by current, right? Voltage divided by current. Then this is the voltage, right? This is voltage. Then what is the current? Okay, before we interpret equation 2, let's introduce Ohm's law in microscopic domain. Okay, the current density equal to the conductivity. Sorry, I confused somebody. Oh, sorry, conductivity. This is a charge. I use sigma as conductivity. Conductivity times electrical field. Okay, This is Ohm's law. Okay, Ohm's law, right? Then if I know the electrical field, okay, if I know the electrical field, then what is this? This is I have a surface, okay, I know the current goes through this surface, okay, then I collect all the normal components because the tangential component won't go through the surface only. So that's why the dot product is very valuable, very useful, right? I always use the dot product to collect normal component, okay, to collect normal component. So that basically I collect all the normal component, okay? So that means the total current goes through this surface. That means the total current. What is this? This is nothing but current. This is voltage. This is voltage, okay? Now you'll find very interesting things. The general definition of capacitor and inductance is associated by this very simple equation, very simple equation. So in another word is, okay, I changed the question for you, okay? I changed the question is, I have two conductors. I have a medium between, but this medium is a lossy medium. Why is it lossy? Because there is moisture, okay, water. Water has conductivity, okay? Moisture has a certain density of water, okay? Then tell me what is capacitance. Then you say, as long as I can find the electrical field, I can find everything, right? Okay, so that is, I can find the capacitance according to this. And also I can find resistance because the permittivity is given, conductivity is given, capacitance you already found, then you know what is the resistance. All right, what is resistance? Say, for example, if you like to find, you say you like to find on your body, okay? You have arm, you put one electrode at one place and another electrode in another place, okay? Sure, this medium is more complex because of my arm, okay? More complex than just homogeneous air. But however, that's still, you can find resistance between the two electrodes, okay, according to this. You find capacitance first, okay, you find capacitance first, right? So that is a general expression that can help us to find resistance, okay, to find resistance. And also, for example, we talk about, we call transmission line. We are going to intensively study this. We have a coaxial cable. Okay, we have a coaxial cable. Actually, my drawing is good, but if ask me to draw on the screen, it's not good. Okay, so I want to find what is the capacitance between the inner conductor and the outer conductor. It's easy, right? You just find the total charge accumulate, okay? Because this is uniform. And then easily you can find the electrical field, okay? For giving voltage or giving charge. Then you can find the capacitance. Once you find the capacitance, you can find what is resistance. Or we can find the conductance because conductance is 1/R per unit length, okay? And we are not interested in infinitely long stuff, okay? Per unit length, if I cut it, okay, with 1, say, centimeter, okay? So I can find the capacitance per centimeter, okay, and the resistance per centimeter. all right? Oh, sorry, we're behind the schedule. Then, okay, let's look quickly. Similar to Coulomb's law, okay, that deal with electrical charge. We can find the Coulomb's law for magnetic field, but we're not calling it as Coulomb's law. We're calling it Power-Savart law, okay? But the concept is very similar, and also was discovered experimentally, okay? Experimentally. What that is if I have a closed loop, then I have a current I2, okay, flowing in a direction, one way or the other, okay? Then I can find if I put another current loop close to it, okay, then I find for a very small section, okay, for a very small section of the current loop 2, okay, then if I take cross multiplication, is because I have DL2. DL2 is what? Differential length, right? Differential length is very important, right? Okay, then the differential length is a vector cross multiply to a distance vector, from one small unit to another small unit on another loop. So this A21 is a vector, is a distance vector, right? The distance is between these two position vector, okay? If this is my coordinate system, right? So if this is this is A1, if this is A2, so this is A21, okay? This is A21, right? This is independent to where I put my coordinate, all right? Okay, then this experimentally discovered this small section of another current loop where I experience a force exert on it, okay? So this force is proportional to these two current, I1 and I2, okay? And also proportional to the length of this current, DL1 and DL2. And also not coincident, it's just created by God. You see, this is also proportional to 1 over 2 square. 1 over R square, okay, 1 over R square. Then the direction of the force that applied to this second loop by following these relations, okay? So you can see this is experimentally discovered, okay? The Coulomb's law for magnetic field. Oh, sorry, right now we haven't defined what is a magnetic field yet, okay? But we find this phenomenon. Force is discovered much earlier than electrical field, magnetic field. Okay, so people always measure the something existence by force. All right. Then also the relation to force is proportional to this, right? So proportionality constant K. The proportional constant K, people found that can equal to mu0 divided by 4 pi. So this is very similar to Coulomb's law. Coulomb's law is 1 over 4 pi epsilon 0. Right? Epsilon is permittivity, so we call mu0, we call permeability. Okay, so, but this permeability in a kilogram and the meter system, okay, that equal to a constant, 4 pi times 10 power of minus 7. All right, okay, this is a constant. This is constant. So under this system, people say compared to Coulomb's law. Compared to Coulomb's law. What Coulomb's law? First, we also experience the force, right? We experience the force, right? Then we found the force is generated by a charge times this quantity we call field. Okay, this quantity we call field. Okay, compared to this, okay. Compared to this, we can say this is something the analogous to Q, right? Then we can define these things to a field. Come in? Yes, right? We can define this as a field. Okay, define this as a field. We call this called magnetic flux density, B. We use symbol B. We officially introduce magnetic field. Okay, then we introduce magnetic field, and according to that experiment, right? According to that experiment, this unlike the Coulomb's law. Okay, Coulomb's law is according to dot product, you can change the order, but for vector product, we cannot do that. Okay, we cannot do that. Right. Then, by introducing magnetic field, we can more concisely express the field, the force according to this. Right. Then, for a given current wire, okay, if we have a current, okay, the current follows the wire direction, but the wire has a direction. So wire has a DL, okay. We use DL, differential length, to describe the direction of the wire, okay. So this is a vector, okay. And also we have a point, if we give a coordinate system. This is a field point, the field point. So if this is a differential length, we have defined a vector. We call this vector the unit vector. We use triangular head. Okay, we use triangular head. So therefore, the magnetic field direction is very clearly defined according to cross multiplication of a vector, right? So that is R cross, the DL cross R, DL cross R. Current direction cross the distance vector, the thumb point to the magnetic field, right? So this can easily explain when we have a coil, right? Say if we have a current go in this direction, or this is DL direction, okay? Let's see the field inside. So we have R, right? If you have a coil, the current goes this direction. So any observation point inside the coil, okay, you see the thumb, that means the magnetic field always inside, right? Always inside. And the everywhere in the coil, the magnetic field inside, the contribute to the field inside, right? Okay, right? So that define, sure, you say the inside, if anything outside of a coil, or anything outside of a coil, you will say this go opposite direction. So that's why we have a magnetic field. This is B inside, then B outside in the opposite direction. Okay, so that is what we say. This is what we say. So all that interpreted by Bhavar's law. Okay, Bhavar's law. So not Coulomb's law anymore. And when we introduce magnetic field, that is related to current. So that's why we have to have a current loop, right? Current loop, because if you only give a segment of current wire, you won't have current. You won't support the current, right? But however, you can treat this F by a very small segment of current. So this, you say, analogous to a charge, a discrete charge. Okay, let's take a break. Let's take a break. So let's take a short break, 10 minutes. Okay, so let's resume. Okay, let's take another look of this Am's law. Okay, before we explain how we make use of it. All right, and we know a force applied to a conducting current wire. All right, and this force generate, okay, this conducting wire carries current I1, okay, in the magnetic field that generate by current 2. So these two current not the same, okay. One current generate magnetic field B, and another current is experience the force, right? Then if we like to vary the force, so if the force change with time, okay, then we have two ways, right? We can either change the current I1 or change current I2 if the location of the two loops are fixed. Okay, location of two loops are fixed. So either we can, the only thing you can change, you cannot change this constant, right? Then the distance you cannot change because the two loops are fixed. So only thing you can change is either I1 or I2. This can be variable. Or you can fix I1, change I2, or fix I2, change I1, right? You don't have to change 2. You don't have to change 2, right? But if you change 2, that will be interesting, okay? Then maybe you see different application you can find. So let's use this example is we change I1 and fix I2, okay? This is what we call loudspeakers, okay? If we look at the loudspeaker, how it works is they use permanent magnet. Okay, permanent magnet, we have south and north terminal. Okay, the end. So that form a fixed magnetic field. Okay, south and north. You see. So we have a fixed magnetic field. Okay, we have a fixed magnetic field from a loop. Okay, so this magnetic field is fixed, right? Then we have a wire wound around a cylinder. Okay, this is a cylinder. This cylinder connects to a movable. Is a moving cone. Is also soft surface. Okay, soft surface. So the current, the coil carry the current I2. Okay, the coil carry the current I2. So why change I2? Why change I2? The change according to our signal strength, right? According to our signal strength, then what we can experience is this coil will experience a force. Okay, then this force change according to the change of I2 with time. And then this cylinder closely attached by this coil. Okay, then this cylinder also is connected to this movable cone-shaped surface. Okay, that is made by just a paper, right? Then that movement moves, change the vibrate the air concentrate inside this cone shape. So that create acoustic wave. That is what we can hear, right? So convert the electrical energy into the air fluid energy. So that is just a simple example. Then I leave the last example for you to read. Okay, it's a very easy example. Is we have an infinitely long conducting wire I put along the z-axis, and then I like to find the magnetic field at any point. So using Poisson law, or you call Ams's law, right? Okay, so let's come to the chapter 2. Chapter 2, we start to learn Maxwell equations, but we study the Maxwell equation in the integral form first. Okay, so Maxwell equation in integral form is a result from the observation of experiment. Okay, a series of experiment. Right. So we also mentioned, you see, this is based on the postulations, right? It's based on the postulation, and the easiest way we can describe the experiment or the observation is using the integral form, because the integral form is more describes the observation in macroscopic. Okay, and then later on, when we want to define the differential form of Maxwell equations, we use a mathematical rule to convert the integral form into the differential form. Okay, so the integral form is more easier. Is easier to understand than the differential form at the beginning. But when we describe Maxwell equation in integral form, inevitably we have to deal with two integrals. One is we call line integral, and another is called surface integral. Okay, line integral and surface integral both deal with vector quantities. Okay. Okay. Then let's take this opportunity to revise what we learned in mathematics. Okay. So first, what is line integral? Right. So line integral. So line integral. Let's assume we have electrical field. We have electrical field exists. This field. So I use field line. I use field line to represent the existence of this electrical field. Then I define an artificial wire which is invisible. Invisible line path, okay, from point A to point B. This line path, this path C, okay, I call the path C. Then I like to conduct a line integration in order to measure how much work I have done by moving a charge, by moving charge Q, okay, from A to B point, okay, moving charge. So by moving charge, okay, then what I do is I measure the work I have done in a number of small sections first and add them together. So this is what I try to do. Okay, so the work done in the first section, or I call delta work. Okay, I call delta work. Okay, then this delta work in section 1, I call delta W1. Okay, the differential or partial work done in section 2, I call delta W2, and so on. Okay. Then how we measure the work is I assume inside this first section, inside this section W1, I assume the electrical field is uniform. Okay, because this section is so small, I can reasonably believe this is acceptable. Okay, so the electrical field in this section 1 is E1. Okay, then the E1 times Q, and because electrical field, I decompose into two components. Okay, in this section 1, one is normal to the path C, and another is tangential to the path C. Okay, two components. The normal component doesn't contribute to the work, because the work I have to only take the force that applied in the same direction as my movement. Okay, so therefore I have to multiply this cosine alpha 1. Okay, this alpha 1 defined here, and then the alpha 1 to make sure I collect the force in the same direction as my path C, right? Similarly, I can collect the work in the section 2 and the section 3 and so on, right? And I add them up, and I can write in a more general case. I can write more in a more general case. Gradually, you see, I write this is E, this is a absolute length of this section G. Okay, then this form I can write in this equation. I can write more concisely using a knowledge we learned about vector multiplication, dot product. Okay, so this dot product is exactly what I described here, right? Okay. Then if I chop this path C into infinite number of small sections, okay, so each small length, the direction and the length is described by the differential length. The differential length, dl. Okay, dl has a direction. The magnitude is infinitely small. Okay, the magnitude difference, but the direction of dl is the direction of my path C, right? Path C. So this is a general way we describe how much work I've done. All right. Let's take an example. Okay, let's take an example. I assume I have electrical field only in the electrical field, only in y direction. Okay, only in y direction. Right. So this is electrical field. Okay, y in y direction. Okay, so that means the strength depend on the location of y, right? If the larger the y, the higher the field strength. So it's just artificial questions. Okay, then we have a charge, okay, with 3 micron coulomb, okay, with 3 microcoulomb, and we like to determine the work done by moving this charge from one point, which is located in the origin A, to the point B. Okay, the B is located in x equal to 1, y equal to 1, z equal to 0. Okay, so that means this path is in the plane x or y plane, right? Okay, according to the definition, we need to do this line integration, right? We know E. Next is we need to express our DL. Okay, the DL in general is delta x in x direction plus delta y in y direction plus z in z direction, right? In that direction, and the good thing is we know this equation. We know this path is y equal to x squared, right? So what is dy? Dy equal to 2x dx, right? So that basically I take derivative on variable x on both sides. Okay, on both sides. Then dz equal to 0, right? Because the curve doesn't change in that direction. Doesn't change in that direction. So we replace the dy by 2 times x dx. Then we can simplify our dl. This is dl. With only variable dx. Only variable with dx. Right. Then this is electrical field. This is E field. This is the dl. This is dot product. All right. So we follow exactly the equation we just found to find the work done. Right. Then at the end, the integrand we can express by this. Then the integration, we substitute this integrand. The integration only carried over x variable. That is from 0 to 1. Okay, so this is a very straightforward. Okay. Now, what is the physical meaning? If the charge we are moving is a unit charge, we define the work done by moving unit charge from point A to point B, we define as a voltage. Okay, the voltage is a very common variable in circuit theory, right? We only have two variables, voltage and current, because all the other quantities can be derived from voltage and current. And also we have a very famous law we call Kirchhoff voltage law and Kirchhoff current law, right? KVL and KCL. That's all defined in terms of voltage. So then you know how important voltage is. But what is the most original definition of voltage? You must understand the field, right? That is the work you have done moving a unit charge from one point to another point. Okay, in an electrical field, this electrical field can be time variant or can be time invariant. That means can change with time or not change with time. Okay, with two different fields result different properties. Okay, let's say this is the most original definition of voltage. Okay, but we didn't stipulate what is the property of electrical field. Okay, then let's say if the path C is somehow come back to the same point, A and B is the same point. Okay, then we do this line integration. We do closed loop line integration. If you say A, this is not A, not equal to B, not exact, but A very close to B. That means I have a very, very small gap. That's fine. You have this freedom, okay, to choose A very close to B, right? You can, in this case, I can say mathematically, this is so close, then I use close, I define as a closed loop, Okay, then in this case, we measure this. When we use a closed loop, we don't call it voltage anymore. We call it the electromotive force. Okay. Electric motive force. Okay. EMF. Okay. We call it EMF if this is related to a closed loop. And interestingly, okay, we can mathematically prove if the electrical field doesn't change with time, this is always true. The EMF equal to 0. Okay, equal to 0. If the field doesn't change with time, we call such electrical field, we call conservative field. Okay, conservative field. Conservative field is what? Is when you're moving a charge in this field in a closed loop, it doesn't take any work. Okay, it doesn't take any work. Then the one example of such conservative field we call that is electric static field. Okay, that is but if this field change with time, if electrical field change with time, then this closed loop integration not necessarily equal to 0. Okay, not equal to 0. And sometimes you see when we move from point A to point B, we define, you see, if this is in conservative field, if the closed loop integration, if the closed loop integration equal to 0, okay, so that means I can define 2 points A and B. Okay, so if this is a path C1, then this is a path C2. Okay, so that means doesn't matter you go past C1 or past C2, if you move a charge from A to B, it doesn't matter. So that is independent to the path. Okay, that independent to the path. So that means this voltage you defined in conservative field is unique. It's unique. It's independent to what path you go. Okay, it's independent to what path you go. Is uniquely defined. So if this is uniquely defined, okay, then the way A to B, what that equal to, we can define is the difference of two potentials. Okay, this difference, the potential, it means the way A is integration goes to infinity. Okay, I go line integration from point A to infinity. Then I go another path from infinity go to B. Okay, so this is a VB is integration from B to infinity. E field here. Okay, because I go from infinity go back to B, so I put a minus sign. Okay, so that clearly define what potential is. Potential is is a voltage between this point, the potential to the potential at infinity. So that's why we call potential at infinity is 0, because potential minus 0 is potential itself. You see, it's a voltage. Right? So if I measure the difference of these two voltage at the 2 points, I define the voltage of these 2 points. Okay, so that is about the EMF, the electromotive force. Okay, that is related to the line integration. Okay, now let's look at surface integration. Okay, the surface integration, in what case we are interested in the surface integration is that suppose I have a magnetic field. Suppose I have a magnetic field. The magnetic field B, right? The B okay, the magnetic field B. Then I like to see how much flux goes through a given surface. Okay, the flux means if I give you this one line, field line, that indicate a flux density goes through a very small surface, right? Then I collect all this magnetic field, goes through the whole surface. Then what I do is, okay, what I do the collection is, I take a normal component again, right? So the B take projection over this normal direction, this direction. How to take projection is the B, the absolute value, the magnitude, dot product, okay? Dot product with this normal direction, or I have projection multiply this cosine, and I times the total area that goes through this surface. This is a flux goes through one surface. If I have n surfaces, I just add them up. Okay, I just add them up, and again, okay, and again, then I write in a vector form. I use a dot product. This define my surface integration. I collect all the flux of B over surface. This surface is open surface. Okay, this surface is open surface. Then next time when you see this surface integration, don't be panicked. Don't be panicked. What that is, it's just addition, right? It's just addition of, I chop this into many small surface. Okay, I find the field intensity. Okay, then I take projection to the normal direction of this intensity B. Take a projection, and I multiply this area, delta S, and I collect all of them on each of these small surfaces. This is what I do for surface integration. Okay, for surface integration. So let's have examples then. Okay, let's have example is, if we have magnetic field given only in that direction, okay, this is easy. I don't need to take, or dot product is easy, right? So that is a function of X and Y. Okay, then we also define an area. Okay. Annoying. Sorry, I don't know how to mute it. Okay, so we have this area, then we have to have a field given. Okay, the field B is given. Okay. Okay, so the field is given. Then let's do a surface integration. And to do this, we need to find a differential area. Okay, because we're doing surface integration, not a line integration. Line integration, we find the differential length. For area, for surface integration, we need to find the differential area. right? In this case, because we assume the normal direction is in positive z direction. Okay, so this is a differential area in rectangular coordinate system. Okay. Then we conduct B dot ds. We conduct B dot ds. Right. So we conduct B dot ds because this is a very simple example. The field B is in z direction, and my ds is also in z direction. So this two unit vector dot product equal to 1, right? Equal to 1. Then we substitute this into this, right? This become ordinary two-dimensional integration. Okay, then we can find flux. Then if this, okay, if this surface integral, if this surface is a closed surface, okay, if this is a closed surface, and we need to define what is the direction of this surface. So if this is a closed surface, okay. Okay, for closed surface, okay, we always define the normal direction is pointing out of the volume. So that depends on, okay, when we define such a surface, okay, that depends on which region is the region we are interested in, okay? And in most of the case, we are interested in a finite volume, right? We're not interested in infinite large volume. So in this case, the n is outward of this sphere or this surface. If in case you are interested in the outside of the world, then you define the direction is inward, so n equal to minus n prime. Okay, so that is opposite direction, right? So this is just a convention. Okay, this is just a convention, and also without we didn't prove this for static magnetic field. For static magnetic field, if B is a magnetic field flux density, this is constantly equal to 0 for magnetic field. If you do surface integration over a closed surface for magnetic field, that is always equal to 0. Okay, so that is what I have today. So we have time for many questions. So anyone can contribute one question. You see, I said you're not helping you. You are helping many of our students by asking questions. Or if this so far is too easy, or I go too slow, no response, no comment. That means it's okay, right? Okay, great. Yeah. Okay, so we will keep this pace. Okay. Then I will give assignment again this week. Okay. I said to some students, why answer questions by email is my job is just keep you thinking. Okay, keep you thinking. Keep you thinking in valuable things, right? And Tan Xiao, have you proposed that question to plot electrical field line for dipole antenna?
I have not.
Okay, so we are going to give a problem, and that is related to Tan Xiao's research, and ask you to plot the electrical field line for small antennas, and then get your interest in this subject. All right. Okay, so if you have no question to ask, so let's stop here today. Oh, don't forget, yes, type your student ID, your name and student ID for attendance check.